Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Natalie Hinkel with us today. Hi, Natalie.
Hi. Nice to see you.
Where are you at today?
I'm actually near, between like Arvada. I'm in Arvada, Colorado, between Boulder and Denver.
Okay.
Yeah.
Okay. What's your home base institution?
I'm normally located in San Antonio, Texas. This was just sort of a temporary thing to kind of get away from the heat for a little while.
Heat, not COVID.
Right. Well, a little bit of both. Yeah, Colorado's been a lot easier, just in terms of the scares, the percentages, things like that. Plus, all the nice breweries have meant that I get to actually go outside for a little while, and that you have like a lot of nice places where you can sit. It's been great, actually. So
Rocky Mountain High.
exactly.
With a beer. That is awesome. Very good. Cool. So, Natalie, what do you like to do for research?
So the majority of my research focuses on stellar abundances, so measuring the elements inside of stars. Put together one of the largest databases of elemental abundances in nearby stars. It's called the Hypatia catalog. In fact, I'm wearing a necklace of what we think Hypatia look like. Yeah, you can't really see it.
Oh yeah, no, I see it. Hopefully there'll be enough resolution, but yeah, no, I see.
Yeah.
Pretty cool.
Yeah, so she's one of the first known female astronomers who lived around 400 AD in Alexandria. She was very well respected, pretty awesome person. So decided to name the database after her. Anyway, so this is
librarian, right? She was head librarian at some point.
I don't actually think that that's true.
Okay.
But what I've read is based on like the few sort of like little things that sort of a remnant of her life, which is actually not a ton because the library burned down. But she actually worked a lot with her dad, which I thought was pretty cool. And she and her dad created the two-dimensional astrolabe. Yeah, which I thought that was nice. Also because my grandmother gave me one right before she passed, and so that was even more meaningful to me.
Wow, very nice.
Yeah. Anyway, so created this database. I've actually been working on it for about 10 years now, which makes me sound old. And what it is I've put together other people's data and smashed it all together into one massive repository of elemental abundances. So at this point, we have about 10,000 stars, all within 500 parsecs, covering 77 elements in all FGK or M-type stars. So I'm focusing specifically on mean sequence stars. And I think in total, we have over 200 different data sets that I've combined and made available to everybody. So not only is it a massive database, it is multidimensional. So there's elements inside of stars measured by different people. Some of those stars have planets. So there's a ton of data. So it's all available online now at hypatiacatalog.com because it is more data than I can handle.
You also catalog kinematic information?
Yeah, I don't catalog it, but I do pull it in from big databases. So so I use like Gaia data, some data from the test input catalog, just to make it easy for people to access the kind of data that they might want to plot. And then I also pull in data from the NASA Exoplanet archive. Right. So that way you can plot stars with and without planets and stuff. So there's a lot there. So I look at the elements inside of stars, and what I've been working on more recently in the last sort of 5-6 years is then connecting those stars to planets. Since stars and planets are made from the same material at the same time, we can take what's in the star and sort of use it to model the interiors of planets. And so I've been working on that with actually a number of collaborators like Cayman Unterborn, not on this paper, but Hilary Hartnett, who is on this paper, Patrick Young, who is on this paper. And so together we're sort of trying to do all of the interdisciplinary things to go from stars to planets to life.
Very cool. And in fact, we're going to cover one of those. Let's go ahead and bring it up. Okay. The influence of stellar phosphorus on our understanding of exoplanets and astrobiology. And Natalie, take us away.
Sure. All right. So I actually kind of like talking about this paper from its inception. Hilary Hartnett and I, we were talking either at a meeting or at in her office or something. we were talking about how we go from stars to planets and sort of what kind of knowledge we can glean from this connection. And so she started. Hillary is an oceanographer, so she started asking about elements that are important for life. So she's like, "Well, what's potassium like?" And I was like, "Oh, we know this much. It kind of looks like this, blah blah blah." And then she was like, "Well, what about phosphorus?" And I was like, "We know almost nothing about phosphorus." And she's like, "What are you talking about?" I was like, it hasn't been measured that much." She's like, "But it's super important." I'm like, "What do you mean it's important?" She's like, "It's important for life. We need it for DNA and RNA and like energy consumption." And I was like, "Really?" I had no idea. And she's like, "Yeah, no, why haven't you guys measured it?" And I'm like, "I don't know, it just hasn't been measured." So that's how we ended up like getting into this paper, was to figure out why uh, why is it hard to measure phosphorus in stars? Why is it so important? And what sort of information can we get out of the little bit that we have? So she actually wrote the beginning of it because obviously I don't know a ton about biology, as I just made very clear. But essentially, what this goes over, so this is sort of the introduction, is how important it is to have phosphorus on Earth. It's absolutely essential for life on Earth that we have phosphorus. And so, as I mentioned, it's in the DNA and RNA, but it also makes up the key elements for life on Earth, which is poorly pronounced as chnops, which is terrible. Yeah, so it's
Chnops, okay.
Yep, chnops. Yeah, it's listed in periodic table order as it should be, but we put it in the parentheticals just to make sure it was clear. But these are all like the super important elements that we need for biology on Earth. To the point where there's actually this ratio of C to N to P called the redfield ratio. So if you scroll down like a smidge to see the equation that's unfortunately at the top of the next page, so this is the equation for photosynthesis. I actually showed this equation at the last AAS winter meeting. I was very proud of myself as an astronomer that I showed a chemical equation to a bunch of other astronomers. So what this says is that you need essentially 106 carbon atoms, add that to 16 nitrogen and 1 phosphorus with some other stuff. So then if you do it in this exact molar ratio, then what you get out is essentially biomass, which is that whole huge thing at the second part of the equation.
Right.
And then the O2 signature that we typically attribute to life. So when people say they're looking for signatures of life in atmosphere, this is where that comes from.
Okay.
So the redfield ratio is important because we need to have all these elements in this ratio in order to produce life. But the problem is that phosphorus is the bottleneck of the whole equation, because on Earth we only get phosphorus by rock weathering. So essentially eroding rocks over time, eventually the phosphorus comes out, and that's how we get it on the Earth's surface. So that ends up being the limiter for this equation. So we wanted to examine this redfield ratio and take it not just for the Earth, but also expand it outwards to Mars. So we looked at the redfield ratio of Mars, and then also other stars to see how far can we extrapolate out, with the idea being ideally once we go and we find stars with planets, terrestrial or rocky planets, that we're actually able to then go from the stellar abundances, try to understand what's in the star. So how closely does this equation match each other? So so if you scroll down a bit, so essentially the whole second chunk of the paper just talks about the Hypatia catalog, which I've already described, and how it combined the data. And the figure 1 is really where we show all of our phosphorus data. So in total, 100 stars in the Hypatia catalog have phosphorus data. So that's a very tiny fraction, very tiny.
What makes phosphorus so hard to measure?
Or
is it easy to measure and people just don't look for it?
No, it's actually incredibly difficult to measure in and of itself. So people do look for it. There are I forgot the number, 7 different groups who've measured phosphorus. So this is what we're looking at, is that's those 7 groups. But the problem is that there's essentially only like so there's no phosphorus lines in the optical band. So that makes it difficult since most telescopes are geared towards the optical. But then there's one phosphorus line in sort of the near infrared, but it's almost exactly at 1 micron, which falls really nicely between where people go to look for optical and where they look for near IR. And so there's this like weird gap in our measurement techniques of exactly where phosphorus falls. There's more lines in the infrared and there's some in the UV as well. But again, most of our instruments aren't catered towards either of those bands. Even the infrared, where there are more spectrographs, more telescopes, unfortunately they're blocked by a lot of the molecules in Earth's atmosphere, so the telluric lines. So it's really hard to measure phosphorus because of that as well. So it's not for a lack of trying. People have actually tried quite hard to get it, but unfortunately it's just really poorly placed as far as the actual observations are concerned. So so you can see from this plot that the majority of the elements that we have, or the phosphorus measurements that we have, are sort of centered around solar, so that's 0.0 dex, with quite a bit of scatter sort of around it. The dex notation is logarithmic. So yeah, so what you're looking at, even though it looks linear, it's actually a log based scale.
Yep.
Yeah. And then they're color coded to show just the distances, which I find it to be kind of interesting. So most of these are fairly nearby.
Cool. Okay, I'm with you.
Yeah. Okay. So so then actually I go into the specifics of how everybody tried to measure it. We do have a combination of people who looked in the infrared and in the UV, but you know, I'll leave those to the citations. Then what we ended up doing is really sort of the more interdisciplinary aspect of the paper. So stellar abundances are measured in dex notation, which is essentially a logged ratio of ratios comparing the amount of that element in the star and then comparing it to our sun and then doing the same thing with another element. I find the notation to be very frustrating and not the most awesome to deal with in general, especially because there are so many different observations of the sun's elemental abundances. So that's a whole mess in and of itself. So to get around this, what we did was we undid the dex notation and we put it as molar fractions. So that's a bit further down. I think we actually get into some of the I think there's an equation where we show it.
Okay, yeah.
Yeah, right there. Yeah, yeah. So that's where we convert from dex to molar fractions. So this is the way to actually see how many individual atoms are we able to deal with, so that we can see how they could react with one another if they were in a planet. So this is actually nice to finally. I realized nobody has published this equation yet on how to go from dex to molar fractions. So we finally got that done, which is nice. In fact, I'm planning on writing a whole paper just going from the overall metallicity of like a galaxy to the individual elemental abundances of stars, then to the molar fractions of their planets, and just walking through the formalism of that because it doesn't exist.
Cool.
Anyway, so this is the starting point for it. Okay, so going back up to that figure. So this figure, we wanted to show, so like I said, we're really focusing on C to N to P, but we wanted to examine what these different ratios look like. And then we threw silicon into the mix since it's very important to life, important to planets, and it was nice to sort of round out the numbers. So, so what you're seeing here are the molar ratios of nitrogen to silicon with respect to carbon to silicon. And so the green circles are all of the stars in the Hypatia catalog. The black triangles are the stars in Hypatia that have planets. And then on top of that, we've overlaid, there's a green, like little clover. It's kind of in the middle. So that's for plankton. That we have the Earth's crust, and then bulk silicate Earth, bulk silicate Mars, and then finally the sun. And then everything else is in the corner. We give actual numbers for these in the table sort of further down, which we don't need to get to yet. So yeah, that's plankton.
Okay, I'm with you. Good.
So we thought this was a really interesting plot to start off with, because there's so much data here. We're looking at 2,800 stars in this one plot, so you can get a sense of like the different patterns that we're seeing. You can actually get a good comparisons of stars with and without planets. To that point, we've actually included the stars with planets in the histogram of this one plot. We didn't do it for the other ones, just to sort of see like how stars with and without planets vary with respect to one another. So they're kind of similar, which is fine. But the interesting thing also is that the sun is quite different to the rest of the stars. So it's way off on the side. The sun is a little bit weird, which not a lot of people realize. But then in comparison, you have all these other planetary components, which are all hunkered down in that bottom left-hand corner. And we were a little surprised by that these weren't as similar to stars with planets as we were thinking that they might be. So that was the real takeaway for this, is just to see how much data there is, see like sort of the rough patterns that we have, and then compare the bulk silicate Earth and Mars and the sun with respect to the rest of the stars with and without planets.
Also drives home the point a little bit. If you normalize to the sun, you're normalizing to something that's abnormal.
Yeah, exactly.
So that can really skew your interpretation.
And this value of the sun, well, yeah, I mean, normally I use ladders at all 0.9, but since we're in molar fractions, it's whatever it wants it to be.
Right, understood. Okay.
Okay, so let's see, where are we? All right, so we can go down to the next figure, which is actually kind of similar, but now we start getting more into the C to N to P. So we can look at this as like 1, because these are actually kind of similar with respect to each other. So the big takeaway from this is that there's not a lot of data here. This is where the having the P, so few P measurements, is actually really frustrating. So I think for both of these plots, we're looking at about 50 data points. And that's because it's not the full 100, because all of these stars, in order to have them on the plot, they have to have phosphorus, nitrogen, and silicon, or in the blue case, carbon, to be able to plot them all. And so not every star has all the elements in them. So that's why we're looking at only about 50. But then, and then what's even sadder is that the number of stars with planets with all of these measurements there's even fewer of them. So I think there's about 12. And so we didn't include them on the histograms. And then the interesting thing that we're seeing from these plots are, again, like where the bulk silicate Earth and Mars are. And then, so they've moved. They're not just slammed in the corner. You can see a little bit of difference.
Yeah, the sun's way up here.
Yeah, the sun's way up there. And then in comparison on the other plot, the sun is in the bottom left-hand corner, and you don't see any of the other ones because they're all over the place.
Right.
So yeah, so this was pretty crazy, because we were expecting the sun to be a little bit more normal, and it really wasn't. If anything, we found that compared to the other stars, the sun is more enriched in phosphorus, and but it's deficient in carbon, which is why. Or wait, no, it's enriched in carbon too. So the P to C made it drop.
Is low, correct? Okay.
Yeah. It took us some time to actually like untangle all these different molar ratios to compare them to one another. All right. So then could we go to the last plot, which is like really our big takeaway message plot.
Okay.
Yeah. Okay. So this is really the whole redfield ratio in one plot. And so we did it in this double layered fashion. So that way you could see finally, and for like the first time, where all of the bulk silicate Earth and Mars actually sit, and how different these scales are. So the big plot that's sort of in the background, you can see where that first where the bulk silicate Earth is, and how different that is from the Earth's crust, which I thought was cool. And then how different these two are from Mars, which is like all the way to the right. And so there's such a huge range.
To be clear, this is a linear scale.
This is a linear scale. Yeah. Yeah, so we were like, whoa, like, this is a pretty intense range, and yet here are all of the stars smushed into this one tiny line that's essentially like right around zero, for P to C, and then like sort of really lightly overlaid, you can see the sun and then plankton. Now, when you go to the blown up version of the zoomed in plot, but we don't have plankton because it's actually slightly to the right. I think, what was the number? Well, I forgot. We listed in the table, but it was too far to show in the zoomed in plot, and still too tiny to show in the background plot, which was pretty funny. But again, you see the sun being pretty weird compared to the other stars, both with and without planets. But there's a pretty like decent range that we're seeing with respect to the P to C and N to C. And so I thought that was pretty interesting, that even for all the phosphorus, the few phosphorus measurements that we have, we're still seeing like a decent range in those values, which say to me that that not only is phosphorus important, which I know, but understanding what the phosphorus is in stars with and without planets is a really big concern, because even as just this, or I guess 50, we see this range. So what's it going to look like when we have, a couple hundred, if not a few thousand? And then what is that going to ultimately mean for the planets? So we ended up talking about that, about a number of these implications. Essentially that the sun ends up being, like I said, phosphorus rich compared to other stars. Doesn't look like that in that plot, but again, it's because of the carbon. But also when I actually took the sun and I put it with respect to like the full 100 stars that we had, it still looks enriched compared to the majority of them. So and then when you have an enriched star, then we have our slightly enriched Earth. The Earth actually has a decent amount of phosphorus, which is good because we as life need it. But when you go to stars that have a lot less phosphorus, what is that going to mean for planets? Because so when stars and planets are forming, when you have this phosphorus, actually the majority of the phosphorus goes into the Earth's core. It gets sequestered there. And so you need sort of a thin veneer of phosphorus on the surface for the life. But if you already start with a little bit of phosphorus, so less than what we have in the sun, then you form a planet. Who's to say if any then would go to the surface? Like maybe it all gets sequestered to the core, in which case there won't be any phosphorus left for life. So, So knowing this and trying to understand it better with better statistics was really the point of this paper, was to sort of show the importance of the phosphorus, and what it means and what kind of information we can get for it, but also like a call to the community of like, please help us get some more data, because it's so difficult, not for lack of trying, but we need to really understand this better, especially in terms of the redfield ratio. And I would like to mention, because like Hillary was very staunch about this, we talk about the redfield ratio and the 106 to 6 to 1, but it doesn't mean that all life has to follow exactly that. It just has to follow roughly that. There can be a variation in the exact numbers, but still, an order of magnitude more for everything. So, so this is the actual table where we give all the numbers, which you've been seeing in the different plots. Everything is normalized to phosphorus, since that's fairly standard in the field. Not our field, obviously, biology. But here we show all the different numbers with respect to one another. And on top of that, we include an average Hypatia star. So this is not those stars that we necessarily showed in all of the plots, since those are the ones that had all the different elements with them, but it's just the full data set of Hypatia stars. So you can see how much those vary from the sun and where the sun sort of sits with respect to all those other ratios. So they're about half.
Wow.
Yeah, I was very surprised by that when I put all the numbers together.
Okay.
Yeah.
Interesting. Interesting. So cool. So very lovely paper.
Thank you.
Very nice. So where do we go from here? Where does the community go from here? Are there new calculations on the way? Are there new telescopes or observational capabilities coming online that could help resolve this?
Well, okay, so there's a number of things, because I've been talking to people. We've been working on this paper for 2 years now, and so I've been talking to a lot of people to get help. So an indirect way that I'm trying to sort of get some help from other people is actually taking advantage of the Apogee survey on SDSS.
Okay. Mm-hmm.
So they observe in a very narrow band in the near infrared. But the interesting part about moving to the infrared is that we don't know every line we see. It actually isn't super well explored, and we haven't been able to identify all the lines. So one idea is to try to use some Hypatia data in order to try to back out if there might be other phosphorus lines in some of the Apogee stars. / they're looking into some more machine learning methods in order to see if they can actually determine phosphorus, which I think would be cool.
I mean, there must be theoretical calculations of the phosphorus atom, right? So people could, in principle, predict where the lines are.
Right, but if we can maybe find some stars that overlap with Hypatia and Apogee and are phosphorus enriched, we might be able to look for other ones like that. So that's part of it.
Okay, so you think that the atomic calculations are in good shape, or?
I think so. Yeah, actually, there's been a number of phosphorus atomic calculations since like the 30s.
Okay.
So I think those are sort of okay.
Okay.
Other thing that I'm working at, actually with Patrick Young, who's one of the co-authors, is that we're putting together a CubeSat that would go after specifically phosphorus. So we would get outside of the Earth's atmosphere, since we would be a small satellite, we would be able to focus on a very narrow band in the infrared. So I think 0.9 to 1.6 is what we're aiming for. And then just be able to do a survey of as many nearby stars as possible to get the phosphorus measurements. And we'd be focusing specifically on FGK type stars. So that's coming up. We're going to be applying for that in November for the APRA. Yeah.
Okay. Nice.
Yeah, but otherwise, just asking people if they have time or energy, especially if they have near infrared telescope access, if they can help us get phosphorus measurements. But I think really when it comes down to it, getting above the atmosphere is pretty crucial. Yeah, so in fact, that's been the driving theme of a lot of my research recently, is just trying to get above the atmosphere.
Balloons.
Yes, exactly.
Ostensibly. Well, that's cool. Very good. So there's a lot of frontiers here in phosphorus. It's not a done deal by any manner of means. In fact, in some sense, the stellar abundance determinations of phosphorus is just getting started.
Yeah, I hope so. That'd be really nice.
Cool. Well, look forward to future papers of yours on this topic of phosphorus.
Yeah, and also other interdisciplinary elements. That's actually a thing I've been trying to work on more, is what are the other elements that we're missing? I was such a surprise when Hillary told me about how much we need phosphorus that I started asking other scientists. I was like, hey, what elements are important for what you do? So I asked like other biologists and planetary scientists, and got back a really interesting collection of elements, some of which I did not anticipate. And so it's not just phosphorus, but fluorine, chlorine, potassium, and nitrogen. Nitrogen, it's been measured about a third of Hypatia stars, but it's still not as many as it could be. Potassium is fairly low, and we have less of fluorine and chlorine.
Yes.
Yes.
Very cool. Very cool. All right, Natalie, thank you so much.
Thank you. This has been really nice.
All right, everyone, and we'll see you on the next one. Bye-bye.